right, so this is the final talk of the evening. It's my great pleasure to introduce literally my oldest friends in the academic world, Shinobu Hosono from Gakushuin University in Tokyo. He and I know each other probably for more than 29 years, close to 30 years. And I'm happy to tell you that I was at his 60th birthday celebration just a few months ago. And thanks to the sort of the pseudo ending of the pandemic, I was able to visit Tokyo and celebrate with Shinobu. So as I said, this is my great pleasure to have him come here today and to tell us about mirror symmetry of abelian fiber Calabi-Yau.
Thank you very much. Okay, so let me start from this slide. Actually, Bohm introduced already. My first work with Bohm is 1995, and when I visited Harvard, and actually I was Professor Yau's postdoc, 92 to 93, and after that, Bohm came to the Harvard as a postdoc. And then around 95, I visited Yau again, and then 3 months, we started collaboration. That was the first one. And then after that, I counted the number, total numbers, up to now, in total, 11 papers we worked with. And as I'm going to talk from now, actually, my interest is, my focus already on goes to the something curriculum, anything curriculum, and that's my focus. On the other hand, Bohn's focus is something much more abstract. He is much more smart, and so he's trying to generalize what the result means or something like that. That's the way our collaboration works. And also the Professor Yau's, on the other hand, is always, I would say, 10 years or 20 years ahead of us, at least ahead of me. So in any case, that's the way our collaboration works up to now. So in any case, thank you very much for enjoyable collaboration so far. It's very nice doing this. So anyway, as I said, my subject today is my focus or my interest is anything cultural. So this is one of them. And then since the 90s, I'm actually the first collaboration around that time. So we are interested in the analysis of period integrals. So usually, and in the period integrals, not one variable, but multi-variables. That means a little bit, a lot of complications to analyze that. And one of the methods is GKC, hypergeometric system, as you know. And similar thing, this time the GKC system doesn't appear, but to analyze period integrals, we have to work on the multi-variables. This time, there's just 2 variables. Nevertheless, lots of structure we can find out. And in the context of if we focus on the mirror symmetries and lots of geometry behind that. That's what I'm going to introduce you today. And I have to say first that I'm going to introduce every aspect of mirror symmetry are encoded in single two parameter and 2 variable non-hypergeometric. So, 2 variable differential system of differential equation of fixed type. So in case the Calabi-Yau manifold, very special Calabi-Yau manifold is of this type. So namely, as you already recognize, I don't know. Maybe just points by hand. So And so as you recognize already here, the very special type of completed section of Calabi-Yau. So here, two completed intersection in project space, 7-dimensional projected space, and very special type of quadratic F1 to F4. And so it just as you see here, the final equation very simple, but nevertheless lots of geometry behind that. So how this special type of complete intersection comes out. So here is the background a little bit. So if some geometry consider the embedding problem of abelian surface with special polarization L. So in this case, the polarization is 1,8 type, and that's defined by this polarization. And then, so given polarization, then we can embed the abelian surface to the certain projected space. In this case, 1,8 case to the projected space we can embed. So the linear system associated this polarization, we are thinking about abelian surface. That means already you recognize data function associated with that. So using that data functions, we will have embedding. So that's that's the first general story. And then the problem around here is that the people maybe are middle 90s or close to 2000, people are interested in the vanishing idea of this image. So consider the embedding of abelian surfaces to the project space, how the homogeneous idea vanishing on the image of this embedding. That's a problem. And then if you look at the entire idea, vanishing idea, then we will recover this abelian variety. But look at some part of that. That's the F1 to F4. That means if you look at the vanishing idea, then the part of that is consists of quadratic like this, and on the other side, and others are higher than degree 3 actually in this case. Degree 3 polynomial exist. They exist to describe the entire function. So that's a story behind this. So in any case, if we consider this type of polarization, actually this kind of problem has been solved by Gross and Press. And then in general, they considered 1,D polarization, and then in general, 1,D, this kind of problem, if you consider, then somehow if you look at the part of the vanishing idea, then as I will explain a little bit more detail, then we will come to this kind of Calabi-Yau threefold. We are starting from a embedding problem of abelian varieties, but if you look at some part of the vanishing idea, naturally we come to the special type of Calabi-Yau threefold. That's a story. So one thing I should say around here is that because of the embedding is given by the data function, because of that, there exists a natural action of Heisenberg group, which comes from the natural. I haven't written here explicitly, but data function on this data function, there is not usually naturally this kind of Heisenberg group action we have. That's some background about this. Here is a summary about the much more geometry about this. As I said, the V omega, VW is W is parameter here. So if we start from fix A, then the parameter W is determined by A. But if we are looking at the only part of that, so just switch the picture, and then in this case W. If we forgot this background, then just focus on these 4 coordinates. Then the omega 0 to omega 2 is just parameter. And then, so if you consider the vanishing locus of these 4 coordinates, that's I'm denote by V sub W. This have some properties. Actually, yes, the W is over there. This defines two complicated intersections. So Calabi-Yau 3-4. Actually, in this form, this is singular. Here it's some property of that V sub W. Heisenberg, first thing is Heisenberg group acts freely on this singular Calabi-Yau VW. And VW is actually the pencil of 1,8 polarized abelian surfaces. So if you look at the vanishing ideal, then it just that gives the abelian varieties. But looking at the subpart of that, so because of that, we'll get the pencil of
so the fiber is the original abelian surface.
Abelian surface, yeah. So here is a description of it. Any case, the parameters of this pencil is not explicit, but and so that part is a little bit very how to say. We have very implicit. So in any case, because of that, because in any case we will have pencil of 1,8 polarized pencil over abelian surfaces, and then also the base points. There are 64 base points of them, and so I mean the situation is something like this. So one parameter family of abelian varieties are described by 4 quadri, and then as a pencil, and then there exists 64 base points of that pencil, and then also these 64 base points gives us the singularity, actually ODP. So one of the 60 base point I described here, and then this direction is parameter P1 as a pencil I described here, and here is the abelian surface. And so this is the parameters, and they move around like this, and this is a base point, one of the base point. That's the structure of this complete intersection. And the point is that the singularity is just this type of 64 ODP. And so because of these singularities, and just we can blow up along the abelian surface, and then after blowing out, we got a small resolution like this, and then just make a plot of this P1, and we got something like this. And so you will see, yeah, originally the parameter for the pencil, and then this is the base point, and then blow up and then make a plot, and we will have this is the parameters for the pencil, and this is the exceptional curve, and then you will see this gives us vibration over this time. That's a structure. So somehow the answer to your Bond's question, the general fiber of this vibration over P1 is the original 1,8 abelian surface. That's a geometry of this Calabi-Yau. And from now I will describe this geometry and small resolution as X. That's an abelian vibration over P. And also originally the Heisenberg group act on naturally on both of the small resolution. And originally the Heisenberg group acted on this singular varieties, Calabi-Yau threefold, but after resolution, this extends to the both of them. So this resolution. So that's a general result by Gross and This study beginning of 2000, beginning of 2001. So in case that's a known result. And so how the Hodge numbers? My interest is the mirror symmetry related to this special type of Calabi-Yau. So you recognize that the after small resolution, originally 2 to 2 complete intersections, and just there exists a hyperplane class from the ambient P7. And then if we consider generic complete intersection, just Calabi-Yau space as just Picard number 1. So just consider complete intersection 2 to 2 for the weeks. But here the special family we started with, and then made a small resolution, and then this abelian surface makes originally that is abelian divisor, but after small resolution, this becomes Calabi divisor. That gives us the Picard number 2 here. And then if we look at the vibration structure, I mean singular fiber, I will describe it. I'll show you structure for the singular fiber, but we have to look at this carefully, singular fiber, but look at the singular fiber, then we will see that the Calabi-Yau space has Euler number 0. So because of that, we will got the Hodge diamond, very simple Hodge diamond like this. So the formation space has 2 dimensions and Picard number 2, and it looks like self-mirror. That's the interesting point. And also, this Calabi-Yau has many interesting properties and studies in several contexts. Another aspect is that, as I explained, this X has admits Z8 cross Z8 actions. So after taking, take some part of this, and then we can take the free quotient X over Z8, and also we can take the full quotient by this free action. The result is that because action is free action, we will obtain smooth Calabi-Yau. So, but the interesting point is that the Calabi-Yau manifold obtained by this kind of free action has a non-trivial fundamental group. Sometimes in the history of Calabi-Yau or mirror symmetries, people are interested in Calabi-Yau threefold with non-trivial fundamental group. And also sometimes people are interested in the Brauer group of Calabi-Yau. And then how the pi1, non-trivial pi1 and Brauer group are related. Sometimes people are interested in this kind of problem. So from that context, sometimes this Calabi-Yau, other people pay attention to this Calabi-Yau. And then, so during that time, Gross and Popes, year 2008, they conducted, they did, actually they calculated the Brauer group for this Calabi-Yau small resolution X, and during that their calculation somehow they conjectured the mirror of this small resolution is this free quotient, and then we consider mirror of this free quotient, and this seems to be full quotient.
Can I also think of all three as Fourier pi-partner?
Is that I'm going to? Yeah. So the Fourier pi-partner is this one, and this one is Fourier pi-partner.
Oh, okay. So they are on the same side.
And this side is not.
That doesn't have another. Okay.
Yeah, seems to be doesn't have. So I mean I cannot exclude totally, but in this context, this is isolated, and these two are Fourier pi-partner features. Yeah, so somehow you already recognize that this feature is consistent with mirror symmetry, and in the sense of homological mirror symmetry. So that's the aspect and known fact kind of history related to this small resolution, special radius threefold. So I'm going to talk this. I'm going to describe the explicitly the family of making family of this Calabi-Yau, and then looking at the modular case of that, and then identifying so-called large complex structure limits, very special type of degeneration point, and then from there I will justify this picture. Or justify or this picture is very in very nice way comes out from the analysis of mirror family, either this one or this one. So that's what I'm going to describe. Okay, so here, as I said, my focus is construct family of from this Calabi-Yau, and then look at the modular space details. So here is the summary what I said. So I started from, maybe it's not precise, but I started from singular special family of 2 to 2 complete intersection into 7, and made a small resolution. That is X. This is not very precise. And then as a definition, spoke locally defined as I described this idea generated by this spoke locally by yes. And then, so as I said, this idea for special form of defined equation as admits symmetry by Heisenberg group. So I described this is Heisenberg group. This idea is invariant under Heisenberg group. Now, what is known is that somehow the people studying abelian varieties, embedding problem of abelian varieties, in that context, it's already known that this Heisenberg group action a little bit extended to larger symmetry group for this idea. So that's I'm describing from now. So to describe that, what is known is that we have Heisenberg group, I mean representation of Heisenberg group maybe precisely that inside the GLHC. Then consider the normalizer there. That's a notation for NH8 here. And then we can describe that this is known facts for people studying abelian varieties. The normalizer of this Heisenberg group is given by S action and D action, and sigma tau is the original generator for the Heisenberg group. A little bit larger group action, we can extend to that larger group. And then to describe symmetry of this idea, I define this representation to GL3C in this form. So how to make this representation is a little bit story, but I'm not going to describe. So just a representation group of homomorphism in this way. So the fact is that as I said, this normalizer actually acts on the defined equation linearly like this. Originally, Heisenberg group acts on the each defined equation invariant way. But this large group acts on the parameter space. So I just define here the representation here 3C. 3 corresponds to the this parameter omega 0, omega naught to omega 3. And then so if you have this larger group on here, then we'll have linear combination. So that means that the idea defined by the equation is invariant under this a little bit larger group. And then here is a little bit more details. So this normalizer and take an image to the GL3C by representation, and then kernel is something.
So the larger group doesn't fix a fiber, right? In the family,
that's a point.
It acts on the whole family.
Whole
the
family.
total space.
Yeah, that's a point. And you are always ahead of me. Any guess? So we have family, the family P2 parameter space and P7, and inside there we have the family. And as I even recognize here, X as a universal family and defining equation as described as a derivative of this idea. And then in this total space, this normalizer acts on this total family. But the question is that if we act on this total larger group, then we will have we can consider quotient, and then by image. So here's a way to look at this exact sequence. So this entire group acts on the total space, and this part acts on the parameter space, and basically this kernel acts on the fiber directions. And then in any case, we will make quotient like this, and then actually we consider quotients by image of rho, and we can find that this is as much where the product is 3 to 1 like this. But the point is that this doesn't have a universal family. The point is this quotient parameterize some isomorphism classes. So to do mirror symmetry, we have defined equation for this family. That's the point. And then so somehow this larger group acts on the total family, total space, but the taking quotient does not give us nice family as a Calabi-Yau to the period integral or those kind of things. So what we have to do is that look at this more smaller group. We have to focus on smaller group of this normalizer, and then we should be able to get and nice family. So here is try and error calculation. There are lots of isomorphisms. Over P2, we have Calabi-Yau 3, 4, but the lots of isomorphic Calabi-Yau appears. So we have to take a quotient to just to parameterize the Calabi-Yau. So larger group is better, but if we take too large, then universal family we cannot expect. So because of that, we consider the larger group which take care of the isomorphism, but still keeping the universal family. That's the problem around here, and they come to this this group. And the subgroup, take this subgroup generated by these two generators, and then take an image. The image becomes very simple, related to P2, and kernel is -1/4. As I said, that this group and sitting center acts on the total space, and this image acts on the parameter space. This kernel acts on the fiber direction. That's nice way to look at this exact sequence. So because the ideal situation is that the quotient of this entire family, and then this acts on the parameter space, and the fiber direction we don't like the group action on the fiber direction to parameterize good families. So because of that, so these are Gilda is pretty nice properties. there exists a little bit smaller group here that looks nice in the sense that if you consider this tau is, I mean, the tau force is, tau is generated as a Heisenberg group. It actually it acts on the total space of X without fixed point. So because of that, so originally we have the family for P2 like this, and the free action we can consider. And this Heisenberg group doesn't have the parameter space, just fiber direction. And so we can think about the quotient, ZA quotient, and then we have, it doesn't act on the parameter space. That means over the parameter space, we have the free quotient of Calabi-Yau. Now, the same thing. So take a tau and sigma, and take a quotient, and then we'll have the family over P2. And then if we consider first step is consider either this or this, and then consider the quotient by this tilde. Then this one is the act on the fiber direction, but already taken the quotient for both. So I mean, for example, this is the quotient, and then this image acts on the parameter space and make a quotient like this. And this kernel acts on the fiber direction. But on the fiber direction, this action is trivial. So that means they have a good family. The same thing for this. So in any case, in this way, we will get a nice family. Here is a summary. Just larger group will put, and starting from the idea, the symmetry of idea, and then as a symmetry, we have large group we can identify. But to get a nice family, we somehow, I looked at the several possibilities, but this G0 tilde is the largest one. So so I'm not exclude any other possibility, but this seems to be the natural one. So in any case, take a G0 tilde, then we will have a nice family over the quotient of P2. And actually, quotient by P2 is the quotient by this abelian cyclic group. So that means we will end up the after taking quotient, we will end up the toric varieties. So any case, we have the family of and family of X over ZA and free quotients of Calabi-Yau over P delta or full quotients Calabi-Yau over P delta. That's the family will come. To became as a natural family to study mirror symmetries. And the answer is yes, this is really nice family. We should look at. That's the answer. So yeah, and guess this. So at this moment, just summary. Just I would say building this to a nice family to look at the mirror symmetry. So accepting these two families as a nice family and look at the Picard's differential equation for the period integral. So as I said, as a parameter space, we'll end up toric varieties, and then toric variety is defined by just the project of the invariant of monomials. This is a toric variety. The point of this toric varieties, just convex arrow of this invariant, and actually singular. This A1 singularity is over here, A1 singularity here, this has A3 singularities, and they can draw a graph like this, and we will end up smooth toric like this. And here I will describe local coordinate, affine coordinate x and y, and then we can think about the differential equation. So here it's as a complete section Calabi-Yau, we can start from this type of standard period integral, Holmes form, and the period integral associated with that, and then look for the differential operators which analyze this period integral. And that's because of this differential equation actually will end up and this the second order, third order differential operators as a pickup differential equations. And actually, we came to two possible possibilities for the family, either the eight quotient or full quotient. And to describe the period integral, so finite group quotient doesn't affect anything. So same thing. So for two families, we will end up to same differential equations. That's a point here. So actually, this as I described around here, actually this differential operators are analyzed by Pavanelli in 2003. So he didn't make a global picture like this. He started around some locus, just some certain fine part he focused, and then he analyzed period integrals and came to the results for the second order, third order differential operators. So here is a little bit picture how the general fiber degenerate over this parameter space.
So how does X and Y related to W? W0, the three variables.
Yes, sorry. I haven't prepared, but the ratio is invariant monomial. Yeah, I'm so sorry, I forgot. It's just take a ratio. And then the Pavanelli already knows that he studied locally around here, and then after drawing out, so actually here I added this line as a discriminant. Somehow some very singularity will observe for the fiber, and so somehow some special boundary point where we can extract mirror symmetry is somehow degeneration is very strong. Maximally degeneration or some those kind of things. So somehow this point is hidden, and then after brought out two boundary points he identified, and then from there he claims that one of the boundary points corresponds to the X, and this one corresponds to the birational model. And when we came to this birational model, and when we take the small resolution. And now we have drawn a picture. So look at again, and then we will start around the same picture, but in addition to this line, actually this discriminant focus, and so you look at carefully, then the discriminant, there is another discriminant focus. So the discriminant focus reduced has two components like this, and then look at the here, and first we take the toric blow up like this, and end up with this boundary point. So these are identified by the large complex limit, mirror symmetry to the X and X prime, like Pavanelli. And if you look at more closely, there exists certain singularities, and somehow, the discriminant touching at the toric devices with certain also the tangency like this, and then for this and grow up 4 times like this, and then end up in the boundary. For this point, just one time and grow up and 2 points. And then the result is that we look at the solution from 0, all these 3 to 4 boundary points are large complex limit, where we can make up the mirror symmetry, and the result is something that's the. So somehow, as I said, the Picard-Fuchs differential equation is the same, but the Picard equation is the icon actually is this one, and then look at the solutions, and I was able to identify boundary point. 6 boundary points, each correspond to the birational model and free die, and for Calabi-Yau I showed at the beginning. So here is summary. If you look at the more closely, so identification, as I summarize like this, and then if you know a little bit mirror symmetry more details, then each boundary point we can make up the integral solution actually. Then if you look more closely the solution around here, then we can divide this boundary point 2 classes. One class is this one and this one. Another one is this one. The difference is that the integral structure. So Picard-Fuchs differential equation is the same, but the integral structure is different. So that corresponds. I have more detailed arguments how to identify the integral structures. So the answer is that the one integral structure is the family I made for this one, and the other integral structure should correspond to this one. So I happen to describe here, but based on the higher genus Gromov-Witten invariant, I can justify identification like this. So this is
so at the level of solution, you're doing an integral transformation from one basis of solution to another basis.
Right.
Right. So you would get many different prediction of probability.
Right.
For different integral structure.
For different integrals. And the identification, so I divided the 2 classes like this, and then this one should correspond to this one. There must be some justification, and that's I have.
And for different integral structure, the Riemann-Roch pairing are also different.
Different.
Yeah.
So here, that time is ending up. So I'll finish just very sketchy description, another aspect of this boundary point. So given a boundary point, we can extract the Gromov-Witten invariant from there. And the Gromov-Witten invariant coming from this one of the boundary points I described here in this table. So here's and also try to interpret in terms of counting curves inside Calabi-Yau. So here is just brief summary. So geometry of H1, that's I said abelian vibration over P1, described at the beginning. If you look at it closely, then the similar fiber, there exist 8 similar fibers. Each of them is so-called translation scroll, and the generic fiber is abelian surface 1,8 type. Going to one of these points was to degenerate. And degeneration type is translation scroll. So elliptic curve and then middle scroll. Something like this. And the Picard group is something like this, hyperplane plus and abelian class of fiber. And then H2 dual to the Picard group is the section of this vibration, and line comes from this translation scroll. I will describe some pictures in data. So in any case, because Picard number 2, every curve class describes as linear combination of section and line like this. this is the prediction coming number from invariants coming from that one, from mirror symmetry. It's in this table. Yeah, it should. And here, if you look at the growth rate, then this is a first or second line is correspond to the one section and two section and three section and so on, and make up the genetic functions for the n section. And then it turns out everything is written by the quasi modular form like this. And eta is eta functions, and the eta to the eighth comes from the singular fiber. And if you know a history of mirror symmetry, this kind of things we observe the elliptic surfaces, that's E string or something like that before. But here we are considering the abelian calculation. Very similar things are happening here. And here is a little bit explanation. So the one section part counts sigma plus L tau counting something like this. And then it comes, this prediction is by yet function. And the 64 comes from the 64 sections. And we just forget about such conducting factors. And it's basically 1 over eta is, and this is an explanation. Then after sigma plus 3L, we can explain these numbers as a counting curve. What are the sigma plus 4L line plus? Some we stacked, and so somehow from n functions we should have certain partition numbers come out. But in this geometry, the explanation geometry, I couldn't explain partition. So that's still I haven't come to the answer. So because of time, let me conclude. I just sketched the entire story. So the point is that that's very special. I introduced you very special type of Calabi-Yau, but nevertheless, I mean the birational model, Boolean chi, and mirror, self-mirror in some sense, all related to Calabi-Yau are put in described by single set of Picard's differential equations. And then from there, we can all kinds of mirror symmetry we can observe. And I just described genus 0 case, but I was able to calculate genus 2. Up to genus 2, I was able to calculate. And then result is again, I formulate the counting function, then counting function described by quasi modular form. Those kind of property exists even for higher genus. Also, the S-duality. So as I said, in case of an elliptic surface, that's fiber-wise Fourier transform the counting problem or Gromov-Witten or Thomas invariant, and by making fiber-wise Fourier, then that transformed one counting problem to the another one, sheaf counting problem. Here we have counting. Here is a result. I showed you the counting problem of curves by fiber-wise Fourier chi. That works in this case too, and then should transform to the S-dual picture and counting problem of sheaf on the abelian fiber Calabi-Yau. That's I don't have any idea. That's the interesting aspect of this. Maybe let me conclude.